Non-covalent interactions cause molecules to be attracted to each other and can result in molecular compounds existing as liquids or solids. There are 5 main types of non-covalent interactions, which are also referred to as intermolecular forces. Those 5 are hydrogen bonding, dipole-dipole, London dispersion, ion dipole, and salt bridge. Today we will be learning about the ion-dipole intermolecular force. Ion dipole is the electrostatic attractive force between a dipole of a polar molecule and an ion or formal charge. The partially positive charge of a dipole is attracted to a negatively charged ion or negative formal charge, and vice versa. The partially negative charge of a dipole is attracted to a positively charged ion or positive formal charge. Before we can get into how exactly this interaction occurs, let's review some of the basic terminology occurring here. Dipoles. Dipoles are physical quantities that not only have a magnitude but also have a direction. Remember that the arrow end of the dipole is pointing toward the negative charge, and the end of the arrow that makes a plus is at the positive end of a molecule. To determine the magnitude of the molecule, you'll need to look it up on the electronegativity value table in Chapter 4. In this force, the dipole is going to be on a polar molecule. To determine if the molecule is polar or not, first we need to identify what kind of molecule it is. For this lesson, let's use water as an example. Water is a small molecule. It has one central atom, oxygen, with all other atoms bonded to the central atom, which are hydrogen and hydrogen. The general rule to tell if a small molecule is polar or not is to look at the atoms surrounding the central atom. If the surrounding atoms are all identical, the molecule is polar. So let's go ahead and draw the dipoles of a water molecule. 2 hydrogens and 1 oxygen. In order to draw our dipoles, we are going to need to look up these atoms on the electronegativity table chart. It's in Chapter 4. When we do that, we will see that hydrogen will have electronegativity of 2.20 and oxygen will have electronegativity of 3.44. Therefore, we know that hydrogen is partially positive and oxygen is partially negative. As I mentioned in the video, when we draw the dipoles, the side of the arrow that has a plus is at the partially positive atom, pointing towards the partially negative. So that's how we would properly draw the dipoles on the water molecule. An ion is a small particle that has an electrical charge. Atoms gain or lose electrons to become ions. Metal atoms can lose electrons to form positive ions, which are called cations. Non-metal atoms can gain electrons to form negative ions, which are called anions. For an example, we have sodium. A sodium atom will lose 1 electron and turn into a sodium cation. For another example, we can see chloride gained an electron to form a chloride anion. Now that we have an idea of how the non-covalent interaction of the ion-dipole force works, let's look at a real-world example. Let's use the same example of sodium and water. After reading the definition of an ion-dipole interaction, we can already assume that it will occur between sodium and water by remembering the basics. We have a polar molecule and an ion. Sodium chloride is a molecule made up of Na and Cl, and it is more commonly known as table salt. It is in the form of a crystal. Water has 2 hydrogens, which are both partially positive, and 1 oxygen, which is partially negative, and as we know, is in the liquid form. So now that we know a little bit about the basics of the ion-dipole force, I'm going to show you a couple examples using some diagrams, and then we're going to try and show it to you a little bit clearer in water. But let's talk about it first. So here we have a water molecule. 2 hydrogens, 1 oxygen, and here I have a plus showing us that hydrogen is partially positive, which is just a closer up view of the dipole, as well as a water molecule, partially negative oxygen on the partially negative dipole. Here we have sodium chloride. We know that they are both ions. We know that sodium has a positive charge, chloride has a negative charge. When these go in water, the positive sodium is going to be attracted to the partially negative oxygen. The partially negative chloride is going to be attracted to the partially positive hydrogen. These are going to the water molecules are going to surround the sodium and the chloride separately, separating them, which is going to cause them to dissolve. Salt is going to cause salt to dissolve in water, and that is basically how the ion-dipole force works. Now we're going to show an example in water. So here I'm putting some water molecules in some water just to give us a better example. Here we have sodium chloride. When sodium chloride goes into the water, it's in the crystal form. So as we talked about before, the partially positive side of the dipole is going to be attracted to the negatively charged ion, which is chloride. Same is true for the partially negative oxygen. It will bond to and surround the positive sodium ion, and they will kind of pull each other away and separate from each other, causing salt to be dissolved in water through the ion-dipole force. So we're going to go over a couple problems. Number one, I'd like you to answer if ion-dipole interactions can occur between magnesium and water. So go ahead and click pause and work on this problem. The answer to this problem is yes. Ion-dipole interaction can occur because we have an ion with the formal charge and the dipole's on a polar molecule, which will have ion-dipole interaction. The second problem I'd like you to work on is, can ion-dipole interactions occur between sulfur dioxide and water? So go ahead and click pause and work on this problem. The answer to number two is no. Ion-dipole interactions cannot occur between sulfur dioxide and water. Although there is a dipole on a polar molecule, here we do not have an ion or a formal charge, so the interaction cannot occur. This moves on to number three. The third problem I'd like you to work on is, can ion-dipole interactions occur between bromide and iodine? So go ahead and click pause and work on this last problem. The answer to number three is also no. Ion-dipole interaction cannot occur between bromide and iodine. The reason being, well, although bromide is an ion with the formal charge, iodine is not a polar molecule, and we know that we need to have a polar molecule and an ion or formal charge for ion-dipole interactions to occur.